Welcome back, design junkies. School taught you to fear failure. The real world will reveal failure is your greatest teacher. This episode of Mechanical Engineering Made Simple comes to you by listener request. If you didn't know, we do those. So if there's a topic you want us to break down, explain, or explore, just drop us a comment. We prioritize getting the content you want in front of you. So let's dive into today's requested topic.
I'm really excited for this one, honestly.
Yeah, it's a huge topic. So I want you to imagine a steel tank, right? Like the size of a school bus, just sitting in the middle of a crowded chemical plant.
Oh, yeah.
And inside, there's this mixture of hydrocarbon gases, and it's compressed so tightly that the vessel basically contains the explosive equivalent of like 500 pounds of TNT.
Easily. Sometimes a lot more, actually.
Right. Now, imagine a microscopic crack, literally no thicker than a single human hair, just hiding at the bottom of a weld seam, right in the middle of that tank. Welcome to our deep dive for today. We are hunting for that crack. We're unpacking the immense complexity, the sheer danger, and the incredibly rigorous safety chain of pressure vessels.
And it really is a chain. Every link matters.
Exactly. Our sources today, they span the entire spectrum of this industry. We've got dense engineering textbooks, historical ASME code documents, and these really gritty, real-world manufacturing guides.
Which I love because you get both sides.
Yeah. Our mission here is to understand the complete picture, from the sterile theoretical design algorithms in the office all the way down to the noisy, sparks-flying reality of the shop floor.
The contrast you just painted there between the theory of the engineering office and the reality of the shop floor, that's the entire reason this industry is governed by such draconian rules.
Right.
I really have to establish the fundamental premise right out of the gate here. Pressure equipment, almost by definition, exists to contain massive amounts of stored energy.
So it's basically a bomb in a box.
Basically, yeah. Whether it's steam or compressed air, volatile chemicals, liquefied gases, the vessel is essentially a barrier. It's holding back a catastrophe.
Okay.
So this entire safety chain will be exploring the design philosophy, the metallurgy, the welding physics, the inspection methods, all the testing and the legal documentation. It all exists for one sole purpose.
To keep the barrier intact.
Exactly, because a failure of that barrier releases the stored energy, and it does not do so gently.
That sets the stakes perfectly.
Yeah.
We are trying to keep a beast in a box.
A very angry beast.
Yeah. But like, when you look at one of these massive steel tanks, say at an oil refinery, it looks utterly indestructible. We're talking steel plates that can be inches thick.
Right, they look like bank vaults.
But our sources repeatedly highlight that these vessels can and do fail. And alarmingly, they often fail at internal pressures well below the theoretical yield strength of the steel.
Which is the crazy part for a lot of people to wrap their heads around.
Exactly. How is it physically possible for a tank to rip apart when the pressure hasn't even reached the material's breaking point?
Well, it comes down to a misunderstanding of what strength actually means, in the context of a fabricated structure.
Okay, break that down for us.
So strength isn't just about the raw tensile capability of a test coupon in a laboratory. It is entirely dependent on geometry, temperature, and operating conditions.
So it's contextual.
Completely contextual. When we categorize vessel failures, they generally fall into four major buckets.
Let's hear them.
First, you have material failures. That's like picking the wrong alloy for the chemical contents or having hidden metallurgical defects from the steel mill.
Okay, so bad ingredients.
Right. Second, you have design failures, using inaccurate load data or maybe ignoring localized stress concentrations.
A bad recipe.
Exactly. Third is fabrication failures. This is the hidden realm, right? Poor quality control, inadequate welding, skipping heat treatments.
The bad cook.
You're nailing the analogy. And finally, you have service failures. That's where the end user changes the operating conditions, pushes the vessel past its design temperature, or experiences a sudden upset condition.
Okay, so the user basically put the cake in the oven at 1,000 degrees instead of 350.
Spot on.
I want to break down the actual mechanics of those failures, though, because the physical ways metal gives up the ghost are fascinating. It's not just a Hollywood explosion every time.
No, not at all. Sometimes it's much quieter, but just as deadly.
Like, for instance, the sources talk about elastic buckling. When I picture that, I think of crushing an empty soda can.
That is the perfect visual.
Right, because you squeeze it lightly from the sides, and it's not that the aluminum tears or rips. The structural geometry suddenly just gives way, folds in on itself, and collapses.
Yeah.
Is that what's actually happening to a massive steel vessel?
That is an excellent way to visualize it. Elastic buckling is a failure of stability. It's not a failure of material
Okay,
strengths.
stability.
Right. It typically happens in vessels subjected to external pressure. Think of a submarine hull, or a vacuum vessel, or even a really tall distillation column subjected to massive wind loads.
Oh, I didn't even think about wind pushing on it.
Oh yeah, wind is a huge factor. The compressive stress causing the shell to buckle and fold inward, it's actually far less than the compressive yield strength of the steel itself.
So the metal itself is fine mathematically, but the shape just quits.
Exactly. The geometry becomes mathematically unstable before the metal reaches its physical limit.
So how do you stop that? Just make the walls super thick?
You could, but that's expensive. Instead, engineers use stiffening rings.
Stiffening rings.
Yeah, they literally weld giant steel hula hoops around the outside of the vessel. It breaks up the unsupported length and prevents that exact soda can collapse.
Okay, that makes sense. A geometric solution for a geometric failure. But then there's brittle fracture, which sounds significantly more terrifying.
Because it is.
The sources note this can happen without any warning, at relatively low pressures, particularly during a hydro test when the water is cold, like around 40 to 50 degrees Fahrenheit.
Yeah, brittle fracture is the absolute nightmare scenario for an inspector.
Why? What's happening inside the steel?
To understand it, you have to look at the atomic lattice of the steel. Most low-carbon steels have what's called a ductile to brittle transition temperature.
Okay, a transition temperature.
Right. Above a certain temperature, the metal behaves in a ductile manner. It stretches, it yields, it deforms before it breaks.
It bends before it breaks.
Exactly. And by bending, it absorbs energy. But if the temperature drops below that transition point, the atomic structure becomes rigid. It can no longer slip and yield.
So it loses all its flexibility.
Totally. So if there is a tiny microscopic flaw, say a sharp notch from a bad weld, and you apply stress.
The material can't stretch to relieve the stress.
Right. The crack initiates and it unzips through the steel matrix at the speed of sound.
Wait, literally the speed of sound.
Yes. The vessel literally shatters like glass. It sends massive shards of steel flying everywhere. There's no bulging, no warning, just instantaneous catastrophic failure.
Shattering like glass. That completely changes how I view industrial steel.
It should.
But what about failures that take years to develop? Because a text mentions stress rupture, and that seems to be tied to a phenomenon called creep.
Yeah, creep is fascinating. It's a time-dependent deformation that happens at elevated temperatures.
Elevate, like how hot?
Say 1,000 degrees Fahrenheit. If you operate a vessel at that temperature, the atomic bonds in the metal physically weaken.
Even if the pressure inside is totally normal.
Yes. Even if the internal pressure is held constant and it's well below the yield strength at room temperature, the metal slowly, imperceptibly stretches over months and years.
Wow, like taffy.
Very slow taffy. The microscopic grain boundaries within the steel actually begin to slide past one another.
And I'm guessing that creates gaps.
Exactly. Eventually, tiny voids form at those boundaries. Then the voids link up into microcracks, and finally the material suffers a stress rupture.
So it's a progressive creeping fracture.
Hence the name, croup.
Right. And if we throw a corrosive chemical into the mix, the sources mention corrosion fatigue. I'm guessing this is a dual threat situation, like the chemical eats the metal and the pressure changes do the rest.
That's exactly the mechanism. It's a localized, synergistic attack.
Synergistic meaning they help each other destroy the tank.
Unfortunately, yes. The corrosive environment creates tiny little pits on the interior surface of the steel.
Okay.
Now, normally, a smooth surface distributes stress evenly, but a pit acts as a stress concentrator. It multiplies the local stress at the very bottom of the pit.
Like a wedge.
Exactly like a wedge. Then, if the vessel experiences cyclic loading, meaning the pressure goes up and down over and over like in a compressor receiver tank.
The tank is breathing, basically, expanding and contracting.
Right. That fatigue initiates a microscopic crack at the very bottom of that corrosive pit. With every single pressure cycle, the crack propagates a fraction of a millimeter deeper.
So it's an accumulation of damage. You start with elastic behavior, where the metal acts like a spring, returns to its shape. Then you hit the yield point, you get irreversible plastic deformation.
The crack initiates.
It propagates with every cycle, and then finally, the remaining wall thickness just can't hold the load and the vessel bursts.
And that entire failure progression, all of those different modes, that is exactly why we can't just guess at how thick a steel wall needs to be based on intuition.
Right, you can't just do a quick back-of-the-envelope calculation.
No. To prevent these different types of failure, engineers need a unified, rigorous philosophy to calculate the invisible forces, the stresses acting on the vessel.
Which naturally leads us to the rule book, the American Society of Mechanical Engineers, ASME.
The Bible of the industry.
Specifically, Section 8 of the Boiler and Pressure Vessel Code. But even within this global standard, our sources highlight a really deep philosophical divide.
Oh, yeah. Division 1 versus Division 2.
Right. From my reading, Division 1 seems to be the old school approach. It's described as design by rules.
Division 1 is absolutely the workhorse of the industry. It's been around for decades.
So what's the philosophy behind it?
The philosophy behind design by rules is basically an acknowledgement that we cannot possibly calculate every single highly localized stress point in a complex geometric shape.
Because it's too complicated.
Way too complicated. We know there are stress concentrations around nozzles at the junctions between the cylindrical shell and the domed heads and at the support brackets.
Sure.
But instead of doing a PhD-level mathematical analysis of every square inch, Division 1 uses a simpler stress model. It's called the maximum principal stress theory.
Okay, maximum principal stress theory. What does that actually mean in practice?
It means we apply a relatively high safety factor. It essentially says, look, we know there are unknown localized stresses, so we will just make the entire vessel wall significantly thicker to absorb them.
Okay, so Division 1 is essentially just throwing more metal at the problem.
Bluntly. Yes.
But surely in industries like aerospace or massive high-pressure chemical reactors where the walls would become absurdly thick, weight and material costs become prohibitive, right?
Extremely prohibitive. You can't fly a Division 1 vessel into space. It's too heavy.
So is Division 2 where they finally break out the heavy calculus to trim the fat?
That is exactly the distinction. Division 2 is design by analysis.
Design by analysis. Okay.
It allows the engineer to use significantly higher allowable stresses, which results in a much thinner wall. And that means massive savings in material weight and cost.
But there has to be a catch.
The trade-off is brutal. In exchange for that thinner wall, the code demands incredibly detailed, highly sophisticated calculations of every single load, thermal gradient, and stress category.
So you can't just hide behind that big safety factor anymore.
Exactly. You have to prove mathematically that the localized stresses are safe. Division 2 also uses a more advanced failure model.
Which one?
Usually the maximum shear stress theory, or the Tresca criterion. They more accurately predict how ductile metals will actually yield under complex, multi-directional loading.
Okay, I have to ask the obvious question here, though.
Go for it.
If Division 1 uses thicker walls and Division 2 uses thinner walls, isn't thicker always safer? Why bother with the complex math and the risk of Division 2 if you can just build a tank with walls that are 5 inches thick and call it a day?
It's a very common assumption. People think thicker automatically equals stronger.
It seems intuitive.
It does. But in the world of pressure vessels, making a wall infinitely thick introduces catastrophic new problems.
Really? Like what?
The first major one is thermal stress.
Okay, thermal stress.
Imagine a vessel operating at 800 degrees Fahrenheit on the inside, right?
Pretty hot.
But the outside is exposed to, say, freezing winter air.
Oh, wow.
If the wall is 5 inches thick, the inside layer of steel expands significantly due to the heat. But the outer layer of steel remains relatively cold and rigid.
Oh, I see where this is going.
The inner metal is trying to push outward, but the outer metal is acting like a vice, crushing it back in.
So the vessel is essentially tearing itself apart from its own internal thermal gradients.
Exactly. The sheer mass of the steel becomes its own worst enemy.
That makes a lot of sense.
Furthermore, thick walls lack flexibility. A pressure vessel needs to be able to breathe, to expand and contract slightly, to absorb pressure shocks or cyclic loads elastically.
And a 5-inch thick wall isn't going to breathe.
A massive, rigid wall can't do that at all. And most importantly, excessively thick walls create severe discontinuity stresses.
I saw that term in the text. Discontinuity stress. How does that actually manifest on the metal?
Let's visualize a very common vessel shape. A cylindrical shell capped with a flat circular head.
Okay, like a giant soup can.
Exactly. Now, the cylindrical shell is relatively thin and flexible, but that flat head has to be incredibly thick to resist bending under pressure.
Right.
When you pressurize the vessel, the cylinder wants to expand outward circumferentially like a balloon.
That makes sense.
But the heavy flat head is rigid. It refuses to expand.
Oh, so at the seam where they meet.
At the weld joint where they meet, the flexible cylinder is physically restrained by the rigid head. The outward expansion forces are diverted, causing the vessel wall to bend sharply right at the junction just to stay attached.
We call this stress redistribution.
Yes.
It's like trying to bend a thick wooden board versus a thin reed. The flexible reed bows with the wind, but the rigid board snaps under the same force.
That's a great analogy. If the wall is incredibly thick, those localized bending stresses at the junction could exceed the yield strength of the material before the vessel even reaches its normal operating pressure.
Before it even hits normal pressure. That's wild.
Which is why understanding the different categories of stress is vital. The ASME code categorizes them into three main buckets:
Let's go through them.
primary, secondary, and peak stresses.
Okay, primary first.
Primary stresses are the big, unrelenting forces. Internal pressure, the dead weight of the vessel itself, the pressure of a massive windstorm pushing against it.
The stuff that isn't going anywhere.
Right. If a primary stress exceeds the yield point of the metal, the deformation won't stop until the vessel bursts or collapses. It is not self-limiting.
And a secondary stress is self-limiting.
Yes. Secondary stresses are caused by restraint, like that thermal expansion we just talked about, or the discontinuity bending at a junction.
So why is it self-limiting?
The key characteristic of a secondary stress is that if it exceeds the yield point, the metal will plastically deform a tiny amount, and that very deformation physically relieves the stress.
Oh, I see. It yields, it reshapes, and it stops pulling.
Exactly. A secondary stress won't cause the vessel to immediately blow up, but if it cycles back and forth over time,
It leads to fatigue failure.
you got it.
Which brings us to the third category, peak stress.
Peak stresses are highly localized spikes in the stress field.
Where do those happen?
They occur at sharp geometric transitions. The corner of a nozzle cutout, a deep scratch on the surface, or the toe of a weld.
So they don't distort the whole tank.
Right, they don't cause gross distortion of the vessel, but they are the exact locations where microscopic fatigue cracks initiate.
And to figure out the baseline, the raw underlying stress across the whole tank, the texts talk about membrane stress analysis. It sounds like they treat the steel like a soap bubble.
That's the baseline assumption, yeah. Membrane stress analysis assumes the vessel wall offers zero resistance to bending.
Zero resistance.
It assumes the forces are pure tension or pure compression spread perfectly uniformly across the entire thickness of the plate.
Which works great for a perfect sphere.
It works beautifully for a perfect, unbroken, thin-walled sphere or cylinder. But the reality is, a vessel needs pipes entering and exiting.
Right, you have to get the chemicals in and out.
The moment you cut a hole in that perfect membrane to weld in a nozzle, you disrupt the lines of force.
How does the stress act then?
The stress flows around the hole like water flowing around a boulder in a stream. It concentrates heavily at the edges.
Okay, so we have these incredibly elegant mathematical models. We understand Tresca, we calculate the primary membrane stresses, we account for the thermal gradients.
It's a lot of math.
So much math. But all of this intricate math assumes that the steel behaves exactly as the textbook dictates.
Right.
What happens when the steel mill sends a bad batch? You could have the greatest engineering design in the world, but if the metal itself is flawed, it's a house of cards.
Absolutely.
How do we actually know what we're building with?
This is a critical transition. We are moving from the pristine world of mathematics to the gritty reality of metallurgy.
Let's get gritty.
The ASME safety chain demands absolute, unbroken material traceability.
Traceability.
You cannot just go to a commercial steel supplier, point to a stack of shiny metal plates and say, I'll take those for my high-pressure reactor.
Even if they look identical.
Even if they look identical. If you cannot prove the metallurgical DNA of that steel, it is legally considered scrap metal for the purposes of pressure vessel construction.
It reminds me of a blood transfusion in a hospital.
How so?
Well, if the label falls off a bag of blood, the nurses don't just look at it, guess that it's typo negative because it's red, and pump it into a patient. The risk is fatal. They throw it in the biohazard bin.
That is a perfect analogy.
Right. With these vessels, if the paperwork gets separated from the seal plate during transit, you don't guess. You can't use it.
The blood transfusion analogy is spot on because the wrong chemistry in the steel can be just as fatal to the vessel.
So how do they label the steel?
The code requires what we call hard stamping on the plate itself.
Literally hammering numbers into the metal.
Literally hammering it. The steel mill stamps a unique heat number directly into the metal, And that number ties inextricably to a specific material certificate.
What's the certificate called?
In European standards, you'll see this referred to as an EN 10204 3.1 or 3.2 certificate. In the U.S., it's a mill test report, or MTR.
And what exactly is on that report? What are the engineers looking for that's so vital?
The MTR is the birth certificate of that specific batch of steel. It documents the exact chemical composition from when it was molten in the ladle.
So all the ingredients.
Everything. The percentages of carbon, manganese, phosphorus, sulfur, silicon, and alloying elements like chromium or molybdenum.
That's incredibly detailed.
It has to be. It also details the mechanical properties proven by destructive testing at the mill.
What kind of destructive testing?
They give you the precise yield strength, the ultimate tensile strength, the elongation percentage, and often the impact toughness at specific low temperatures.
I imagine the carbon content is a huge factor there.
Oh, massive.
Because if a mill accidentally sends a plate with a slightly higher carbon equivalent than specified, it might still look like the right steel, but once the welders hit it with an arc, the chemistry takes over.
Exactly. Higher carbon makes steel harder and stronger, but it also makes it vastly more susceptible to cracking when rapidly cooled.
Which is exactly what happens during welding.
Right. If you design a vessel, assuming a low-carbon, highly ductile steel, but you accidentally build it with a higher carbon plate,
The thermal shock of the welding arc will create microscopic brittle fractures all along the weld seam.
the vessel is compromised before it even leaves the shop.
The sources mention that the rules for substituting materials are really rigid, too.
Very rigid.
Say a fabricator is building a vessel, and they run out of the specific high-strength steel specified for a reinforcing pad around a large nozzle.
Happens all the time.
Can they just grab a lower-strength carbon steel off the rack to keep production moving?
They can, but there is a severe mathematical penalty.
A penalty.
Yeah, the code dictates that if you use a lower strength material for reinforcement, the area considered as effectively reinforcing the cutout must be decreased proportionately by the ratio of the allowable stress values of the two materials.
Wait, say that again?
Basically, you have to use significantly more of the weaker steel to achieve the same result. You have to make the pad much bigger or thicker.
Oh, I see.
Furthermore, when you weld two dissimilar metals together, the design calculations must assume the weld joint is only as strong as the weaker of the two parent materials.
So you never get to claim credit for the high-strength steel if its weakest link is the material it's attached to.
Never. The math won't let you.
It's an incredibly strict system.
Mm.
But it makes sense. So we have the verified, documented steel. We know its chemistry. Now comes the most physically violent part of the entire manufacturing process.
Melting it down.
Belting it down and joining the pieces together. Let's talk about the welding.
I'm glad you framed it as physically violent.
Because it is.
It really is. And we need to dispel the notion that welding is just a high-temperature form of gluing.
It's not just melting two things so they stick together.
No, it is a fundamental metallurgical transformation. You are using massive electrical energy to create a localized pool of molten metal. You're essentially creating a miniature, rapidly cooled casting that bridges two wrought plates.
A miniature casting. That's a great way to put it.
Because the physics of that phase change are so volatile, welding is heavily governed by ASME Section 9. You can't just hand a welder a stinger and tell them to fill the groove.
Our textbooks talk extensively about the WPS and the PQR.
The holy texts of welding.
They seem to be the foundational documents for any weld on a pressure vessel. What are they actually controlling?
So the WPS is the welding procedure specification. Think of it as the ultimate hyper-detailed recipe.
A recipe for the weld.
Exactly. It dictates every single variable of the weld. It specifies the exact angle of the joint bevel, the specific classification of filler metal, the type of shielding gas, the electrical polarity, the voltage, the amperage, and the travel speed of the torch.
That is a lot to keep track of.
And that's not even all of it. It also dictates thermal controls, like the minimum preheat temperature of the steel before the arc strikes.
And the maximum interpass temperature between subsequent layers.
Yes.
Right. I want to pause on that preheat thing. Why do they care so much about the temperature of the steel before they even start welding? Isn't the arc thousands of degrees anyway?
Because of the cooling rate.
The cooling rate.
Yeah, if you strike an arc on a massive cold piece of steel, the surrounding metal acts like a giant heat sink.
Oh, it just sucks the heat right out of the puddle.
Instantly. It quenches the molten weld pool almost instantly.
And quenching is bad.
Very bad. That rapid freezing traps hydrogen gas in the atomic lattice. And it forms a very hard, brittle microscopic grain structure called martensite.
Martensite. Okay.
By applying warming the massive steel plates with giant propane torches or electrical resistance bands before welding, you slow down the cooling rate.
So it cools gently.
Right. You allow the hydrogen to diffuse out and you allow the steel to form a softer, more ductile grain structure.
The WPS is the recipe to control that specific metallurgy.
Exactly.
But a recipe is useless if you haven't proven it actually tastes good.
Right.
That's where the PQR comes in, right?
Right. Yes. The PQR is the procedure qualification record. It is the empirical proof.
How do they prove it?
To get a PQR, the manufacturer has to take 2 test plates of the exact material, weld them together in a lab using the exact parameters of the WPS, and then cut that weld apart and test it to destruction.
Test it to destruction.
They pull it in a tensile machine to prove it meets the required strength. They bend it to prove its ductility. If the test piece passes, the PQR becomes the legal document validating the WPS.
And even then, the welder themselves has to prove they have the physical dexterity to follow the recipe, right?
Right. The welder has to pass a performance qualification test.
Making a test weld in a specific position, like vertical or overhead, to prove they can control the molten puddle against the pull of gravity.
Exactly. And the level of control required varies heavily depending on the process. The sources mention several. SMAW, which is shielded metal arc welding, commonly known as stick welding.
Stick welding.
Then there's FCAW, flux cord arc welding. GTAW, or TIG welding. Each has totally different heat inputs and deposition rates.
But regardless of the process, the welder's constantly battling the formation of microscopic defects.
Always. It's a constant battle.
Let's talk about those defects, because the terminology in the sources is very specific. They're hunting for porosity, lack of fusion, inclusions, and undercut.
The big 4.
How do these actually form in the puddle? Let's start with porosity.
So porosity is basically trapped gas bubbles.
Like carbonation in a soda.
Yeah, exactly like that. If the shielding gas gets blown away by, a draft in the shop, or if the metal is contaminated with oil or moisture, gas forms in the molten puddle.
And it freezes before it can escape.
Right. If the puddle freezes before the gas can bubble out to the surface, you're left with these spherical voids right inside the weld.
Okay, what about inclusions, slag inclusions?
Slag inclusions happen when the glassy flux coating that protects the weld isn't properly chipped and wire brushed away between passes.
So the welder just welds over the dirt.
Basically. The next layer of weld traps that non-metallic slag inside the joint.
And lack of fusion. That sounds like the weld metal just didn't melt into the side of the plate.
That's precisely what it is. If the welder's travel speed is too fast or the amperage is too low, the molten filler metal flows into the joint but fails to melt the adjacent base metal.
It's like dripping hot candle wax onto a cold table.
Great visual. It sits there, but it's not bonded. It creates a planar defect.
Essentially an internal crack.
Exactly. But arguably the most dangerous defect of all is lack of penetration, particularly at the root.
The root is the very first pass, right?
Yeah.
The bottommost layer of the weld.
Right. Often on the inside of a vessel where it's incredibly hard to see.
So what happens if they miss the root?
When you bevel 2 thick plates to form a V-groove, the root is the narrow gap at the very bottom. If the welder's arc doesn't penetrate all the way through that gap to melt the bottom edges together, you are left with a sharp, unwelded linear notch running along the inside of the vessel.
And going back to our discussion on peak stresses.
A sharp notch is the ultimate stress concentrator.
It is the perfect initiation point for a fatigue crack to grow right up through the center of the weld.
Precisely.
I read about how they actually verify the metallurgy of these production welds, and this is where it gets really intense.
Oh, the test plates.
Yeah. They don't just rely on the initial PQR. For high-stakes vessels, they use production test plates.
Right.
They literally tack an extra piece of steel plate onto the end of the vessel seam, run the welding machine right through the vessel joint and out onto the test plate, cut the plate off, and send it to a metallurgical lab to be destroyed.
They do that because they need to verify the heat-affected zone, or the HAZ.
The HAZ. Oh, you touched on this with preheating.
Right. The parent metal directly adjacent to the weld pool doesn't melt, but it is subjected to incredibly high temperatures and then rapid cooling.
So it bakes it.
It bakes it, and this thermal cycle fundamentally alters its microscopic crystalline structure. The HAZ is almost always the weakest link in a welded joint.
So they take this test plate and they subject it to transverse bend test. They force the welded sample into a tight U-shape around a steel former.
The bend test is ruthless.
I bet.
The outer fibers of the bend are subjected to massive tensile strain. The inspectors are closely examining the surface of the HAZ during the bend.
What are they looking for?
They're looking for any tearing, crazing, or microscopic fractures. If the HAZ has become too hard and brittle due to improper heat input, it won't stretch around the former.
It'll just snap.
It will simply snap.
They also physically polish a cross-section of the weld until it shines like a mirror, and then they etch it with nitric acid. This blows my mind.
It's called macro etching.
The acid actually reveals the microscopic grain structure to the naked eye.
Yeah, the acid attacks the boundaries between the microscopic grains of steel. Because the grain structure of the cast weld metal is different from the heat-altered grains of the HAZ.
And different again from the unaffected parent metal.
Right. The acid etches them at different rates. Suddenly, the distinct zones reveal themselves visually as dark and light bands.
And once they can see the zones, they attack it with a diamond-tipped indenter to measure the Vickers hardness.
Yes, physically measuring how hard the steel has become in each specific microscopic band.
Hardness is a direct proxy for brittleness and tensile strength, right?
Correct. If the HAZ hardness spikes too high above the parent metal, it indicates a highly susceptible microstructure.
Susceptible to what?
Well, in certain severe chemical services, like wet hydrogen sulfide in a refinery, a hard HAZ will absorb atomic hydrogen from the process fluid and literally crack wide open in a matter of hours.
Hours. Wow.
If the test plate fails that hardness check, the manufacturer might be forced to apply post-weld heat treatment, or PWHT.
What does that involve?
Heating the entire vessel in a massive furnace to like 1100 degrees to temper the steel and soften that HAZ.
All of this science is incredible, but reading the textbooks, you get the sense of this perfectly controlled laboratory environment.
Which is not reality.
Exactly. Our manufacturing guys tell a very different story. Out on the shop floor, you have a massive 10-ton cylindrical shell hanging from a crane. It's cold, it's loud, and reality violently clashes with the CAD drawings.
It's chaos compared to the lab.
Why does the shop floor struggle so much to match the engineering theory?
Because steel has a memory and it fights back.
Steel has a memory.
Yeah. An engineer can draw a perfectly circular, mathematically flawless cylinder on a screen, but you have to physically create that cylinder by feeding massive, flat steel plates through heavy rolling machines.
Right, you have to bend it.
And the laws of physics conspire against perfection here. When you roll a thick plate, say over an inch thick, the outer fibers yield in tension and the inner fibers yield in compression.
Okay, that makes sense.
But the core of the plate remains elastic. When the plate exits the rolls, that elastic core tries to return to its original flat shape.
Oh.
The cylinder springs back, it opens up. It is never perfectly round.
And what about thin plates? If thick plates fight the bend, do thin plates cooperate?
Thin plates present the exact opposite problem. A thin plate, maybe 3/8 of an inch thick, rolls very easily, but it lacks structural rigidity.
So it's floppy.
Yes. The moment you introduce the intense, localized heat of a welding arc along a longitudinal seam, the metal expands and contracts unevenly.
Because it's too thin to hold its shape.
Exactly. The thin cylinder warps, twists, and distorts like a potato chip under the thermal strain.
A steel potato chip.
Basically.
So you have these imperfect, slightly warped, out-of-round cylinders, and you have to fit them up to large, heavy domed heads.
Right.
The engineering drawings say they made perfectly flush. The reality on the floor is that there's a gap on one side and an overlap on the other. How do the fitters solve this?
This is where we run into what the sources call shop floor sins.
Ooh, shop floor sins. I like that.
The correct, tedious way to fix an out-of-round shell is to re-roll it, or carefully apply localized heat shrinking.
Which takes time.
A lot of time. The fast, dangerous way is to force the fit.
Forcing it.
The fitters will weld massive steel cleats to the shell and the head, hook up 10-ton hydraulic jacks and chainfalls, and literally crush, push, and stretch the steel until the edges align.
Just brute force.
Pure brute force. Then, while the steel is screaming under all that hydraulic tension, a welder quickly lays down heavy tack welds to lock it in place.
It's exactly like forcing a zipper on an overstuffed suitcase.
Oh, that's exactly what it is.
You lean all your weight on the suitcase, you yank the zipper closed, and you step back. It looks closed. It looks fine on the outside.
But the tension.
Right. The static tension pulling on those zipper teeth is enormous. The structural integrity is compromised before you even pick up the bag. It guarantees it will burst at the slightest shock.
That analogy perfectly captures the danger. When a shop forces a vessel together, they are locking in massive discontinuity stresses.
Just from trying to assemble it.
Yeah. The steel is yielding just trying to hold its own fabricated shape.
Yeah.
You have eaten up a massive portion of the vessel's calculated safety factor before it has ever seen a single drop of internal pressure.
I read that the ASME code is well aware of this tendency, which is why they have extremely strict misalignment tolerances. They don't just say make it flush, they quantify it.
Yes, the code dictates allowable offset. The acceptable surface misalignment between two plates is strictly limited to a fraction of the plate thickness.
For example.
For longitudinal seams, which experience double the stress of circumferential seams, the tolerance might be limited to 1/4 of the plate thickness, or E/4.
So if it's an inch thick, you only get a 1/4 inch of wiggle room.
Right. If a shop exceeds that offset, the lines of stress cannot flow smoothly across the joint. The stress concentration at the misalignment becomes a structural hazard, and the inspector will force them to cut it apart and refit it.
Cut the whole thing apart.
Yep.
But if an inspector is coming and the weld looks ugly or the plates are slightly offset, there's another sin the guides warn about: excessive grinding.
Grinding is the fabricator's eraser.
Ooh, that sounds bad.
It can be. If a welder leaves undercut, which is a sharp groove melted into the base metal at the toe of the weld, the temptation is to just take a heavy grinder and feather the base metal down until the groove disappears.
Because it makes it look smooth.
Right, it makes the weld look smooth and beautiful. But by doing so, the grinder has physically removed base metal.
Oh, they've thinned the wall.
Exactly. They have reduced the effective wall thickness of the vessel below the engineer's calculated minimum.
Right.
They've hidden a cosmetic flaw by creating a localized, thin spot that cannot handle the primary membrane stress.
It's terrifying how easily a quick fix with a grinder can invalidate months of engineering math.
It just takes a few minutes with an angle grinder.
And it's not just the main seams that warp. The sources highlight the struggle with nozzle flanges, too.
Nozzles are notorious.
Why are nozzles so bad?
Well, you cut a large hole in a curved shell, weld in a heavy pipe, and cap it with a thick flange. As that massive volume of weld metal cools, it shrinks dramatically.
And that shrinkage moves the pipe.
It literally pulls the nozzle out of plumb. The flange face is no longer perfectly parallel to the vessel's center line.
So it's pointing the wrong way.
Slightly, yes. The shop might not care, they just ship it. But when the vessel is installed in the field, the piping crew has to bolt a rigid 12-inch process pipe to that skewed flange.
And they aren't going to send it back.
No, they use chain falls to yank the heavy pipe over to meet the flange.
Oh.
Now you have massive external bending moments permanently loaded onto that nozzle, completely invalidating the original stress calculations.
So, because of all these human factors, production pressure, fatigue, the physical realities of rolling steel, force fits, hidden grinding, just visually looking at the outside of the vessel is nowhere near enough.
Not even close.
A smooth weld could be hiding a canyon of lack of fusion inside. We have to look through the metal.
Through the metal.
Which brings us to the realm of non-destructive examination, or NDE, governed by ASME Section V.
Section V has a fascinating, somewhat chaotic origin story.
The end cases, right?
Yeah. Back in the mid-20th century, with the dawn of the commercial nuclear industry, there was a massive proliferation of what they called N cases, special code cases for nuclear construction.
Okay.
At the time, Section 1 for boilers, Section 8 for vessels, and Section 3 for nuclear components were all developing their own slightly different rules for how to shoot an X-ray or bounce an ultrasonic wave.
That sounds like an administrative nightmare.
It was. To solve it, ASME extracted all the physical methodologies and consolidated them into a single centralized code, Section V.
But the deeper I read into Section V, the more I realized it's kind of incomplete. It doesn't actually tell you if a vessel is safe or if a weld is rejected.
That's a crucial distinction. Section V is strictly a methodology code. It provides the physical parameters of the test.
So it tells you how to test it.
Right. It dictates how to calibrate the ultrasonic machine, what chemical sensitivity the dye penetrant must have, or what the maximum kilovoltage of the X-ray tube should be based on the steel thickness. It ensures the quality of the examination.
But it doesn't give you pass or fail grades.
Absolutely not. Section V has 0 acceptance criteria. It will not tell you if a 2mm slag inclusion is a pass or a fail.
Where do you find that out?
For that, you have to return to the referencing construction code, like Section 8, which evaluates the flaw size against the mathematical design factors. Section V is just a toolbox.
Okay, so let's look at the tools inside that box.
Hmm.
Obviously, visual examination is the most common, but our sources note it's historically been the least rigorously documented.
Sadly, yes.
It checked for the obvious surface sins: dents, deep arc strikes, aggressive grinding, and weld profile issues like excessive convexity that creates sharp stress risers at the toes.
But visual can only do so much.
Right. To find the truly invisible surface flaws, we move to things like dye penetrant, or DP. How does spraying some liquid on steel find a microscopic crack?
It relies entirely on the physics of capillary action.
Capillary action.
Yeah. You start by thoroughly cleaning the metal surface. Then you spray on a highly fluid, brightly colored red dye.
Okay, red dye.
Because of its extremely low surface tension, capillary action pulls this dye down into microscopic surface-breaking cracks. Cracks as tight as 1/10 of a millimeter. Far too small for the human eye to see.
Then what? You just look for red lines.
Not yet. You let it dwell, then carefully wipe the excess red dye off the surface so the surface looks clean.
But the dye is still in the crack.
Exactly. Finally, you spray on a chalky white developer. The developer acts like a chemical sponge. It reverses the capillary action, sucking the trapped red dye out of the cracks and bleeding it into the white developer.
Oh, that's brilliant.
Isn't it? The microscopic crack suddenly appears as a glaring, vivid red line against a stark white background.
That is beautifully simple physics. And magnetic particle inspection, MPI, does something similar for carbon steel using magnetic fields, right?
Yeah, MPI uses magnetism to pull iron powder into surface flaws.
But DP and MPI can only find flaws that physically break the surface.
Exactly. Surface flaws only.
To see deep inside the wall thickness, to find that deadly lack of root penetration or trapped slag, you have to use volumetric NDE, radiographic testing, RT, and ultrasonic testing, UT.
Radiography works exactly like a medical X-ray, just on an industrial scale.
It's a big X-ray machines.
Yeah, for steel up to about 6 inches thick, they use X-ray tubes. But for much thicker sections, they have to use incredibly dangerous radioactive isotopes,
Like what?
like iridium-192 or cobalt-60, emitting high-energy gamma rays.
That sounds intense.
The technician places a photographic film on one side of the weld and the radiation source on the other.
And from what I understand, the X-ray is actually looking for missing density, right?
Exactly. Radiation is absorbed by dense matter. Solid steel absorbs the rays, so the film behind it stays relatively light.
Okay, so solid steel is light on the film.
Right, but if there is a gas bubble porosity or a pocket of light, non-metallic slag trapped in the weld,
Radiation hits the bubble.
and passes right through that void, burning the film darker. So volumetric defects show up as dark spots or dark lines on the radiograph.
But X-rays have a blind spot, don't they?
A very dangerous one.
If you have a razor-thin lack of fusion defect, a crack where the metal didn't bond, but there's no actual gap or void, and the X-ray beam hits it straight on.
The radiation passes through the surrounding steel and completely misses the crack.
The film looks clean, but there's a lethal defect inside.
Which is terrifying. And that's exactly where UT ultrasonic testing shines.
So how does UT work?
You've hit on the exact reason why modern codes increasingly favor UT. Ultrasonic testing uses a transducer to fire high-frequency sound waves, often at a shear angle deep into the steel.
Sound waves.
Yeah, sound travels perfectly through solid, homogeneous metal, but the moment the sound wave hits a planar defect, an acoustic boundary like a lack of fusion crack or a delamination, the sound wave bounces back.
Like sonar.
Like sonar. The technician watches an A-scope screen, and they see a massive spike in the echo return. UT is incredibly sensitive to those deadly, planar, crack-like defects that RT might miss.
And the codes are strategic about where they force you to look. Section 8 doesn't always demand 100% radiography. They have rules for spot radiography, taking samples of the wells.
Right, to save time and money.
But those spots aren't picked at random. The inspector can't just pick the easiest, smoothest part of the weld to X-ray.
Not at all. If a vessel design allows for spot radiography, the code dictates that those spots must include the intersections where the longitudinal weld seams cross the circumferential weld seams.
The T-joints.
Exactly. Those four-way intersections are the most highly constrained, complex stress points in the entire cylinder. The code also targets the welds near heavy nozzle reinforcements. You hunt for trouble where the geometry tells you trouble is most likely to initiate.
But even with all the sound waves and gamma rays in the world, you're still just taking pictures and looking at echoes.
It's all theoretical until the final step.
Right. At some point, You have to step away from the theories, the film, and the math, and actually prove that the steel can hold the pressure. You have to fill the beast.
The pressure test.
Let's talk about the final trial, the hydrostatic, pneumatic, and leak testing.
This is the moment of truth. But we really need to clarify what a pressure test is and, more importantly, what it is not.
Okay, clarify it for us.
When we perform a hydrostatic test, filling the vessel with fluid and raising the internal pressure to 125% or 130% of its maximum allowable working pressure, we are performing a static stress test.
Static, meaning it just sits there.
Right. The primary goal is to prove gross structural integrity and to ensure there are no leak paths through the thickness of the metal.
Right. I've heard some people mistakenly think the hydro test is supposed to, shake out the bad welds or somehow validate a vessel that they know has questionable x-rays.
You hear that all the time on the shop floor.
You can't just say, well, the UT showed a massive lack of fusion crack, but it held water for an hour, so ship it.
Exactly. A hydro test is not a fatigue test, and it is absolutely not a substitute for NDE.
Because it doesn't cycle.
Right. A critical lack of fusion defect might easily survive a single slow static load during a hydro test, only to propagate and fail catastrophically 6 months later under cyclic thermal loading in the field.
The hydro test is the final verification, not a diagnostic tool.
Well said.
And the choice of the test medium is literally a matter of life and death. The standard is hydrostatic, using water. Why water?
Because water is practically incompressible.
Meaning you can't squish it.
Exactly. Its volume changes infinitesimally under pressure. When you pump a massive vessel full of water to 1,000 psi, the energy stored inside is relatively small.
So if it breaks?
If the worst happens, say a major weld seam splits open at peak test pressure, the water immediately expands by a fraction of a percent, the pressure drops to zero instantly, and the energy dissipates.
There's no explosion.
You get a loud bang, a split seam, and a very wet floor. It's a failure, but it's rarely a fatal disaster.
But then our sources detail the alternative. Pneumatic testing. Testing the vessel using compressed air or nitrogen gas. The warnings surrounding this are severe.
Terrifyingly severe.
They treat pneumatic testing like building a bomb in the middle of the shop. Let's break down the physics of why air is so much more dangerous than water.
It comes down to thermodynamics and Boyle's law. Unlike water, gases are highly compressible.
You could squish a lot of air into a small space.
A huge amount. When you pump 1,000 cubic feet of air into a vessel and compress it to 1,000 psi, you are forcing the gas molecules tightly together. The gas acts like a giant, invisible, coiled spring, storing massive amounts of potential energy.
So what happens if a seam splits then?
If a weld seam fails during a pneumatic test, the pressure does not drop instantly. The highly compressed gas violently and continuously expands, tearing the crack wide open, ripping the steel apart, and propelling heavy metal shrapnel outward at supersonic velocities.
Supersonic.
Yes. A pneumatic failure doesn't just make the floor white. The shock wave levels the building and destroys anything in its path.
So if pneumatic testing is effectively manufacturing a bomb, why would any sane engineer or shop manager ever authorize it? Why not just use water every single time?
You only authorize a pneumatic test when the laws of physics or the demands of the chemical process leave you absolutely no other choice.
Give me an example.
Consider a massive distillation column designed for a petrochemical plant. Because of its immense height and thin walls, the foundation and the vessel skirt are designed to support the weight of the steel and a lightweight hydrocarbon gas.
Okay, light gas.
If you try to fill that column to the top with water for a hydro test, the dead weight of the water column is so immense that it would literally crush the bottom of the vessel or collapse the foundation.
Wow. The test medium is heavier than the operating medium?
The structure physically cannot hold the water.
What about process contamination? Is that a factor?
That's the second major reason. Some vessels are designed for cryogenic services or highly reactive chemicals, where introducing even a microscopic film of residual moisture from a hydro test is unacceptable.
Because water causes rust.
Rust, yes, but also violent reactions. Even if you try to dry it out with hot air, trapped moisture in crevices could cause massive corrosion later, or trigger a violent chemical reaction when the process fluid is introduced.
So you have to use gas.
In those cases, you must test with a clean, dry, inert gas like nitrogen.
And because of that bomb-like danger, the precautions are extreme. The code demands that every single weld gets 100% volumetric NDE and 100% surface crack detection before you even hook up the compressor.
Before you even turn it on.
You clear the shop floor, establish blast zones, and raise the pressure in slow, incremental stages to allow the steel to strain and settle.
Precisely. You don't take chances with stored volumetric energy. The sources also touch on vacuum leak testing, which is a completely different paradigm.
Right, for things like power plant surface condensers.
Yeah.
You aren't testing for bursting strength. You're testing to ensure outside air doesn't leak in and ruin the vacuum.
Yes. In those cases, a hydro test won't find a microscopic pinhole leak.
So how do you find it?
They pull a deep vacuum on the vessel, and then a technician goes around the outside of all the welds with a wand, spraying a fine mist of helium gas.
Helium. Why helium?
Inside the vacuum system, a mass spectrometer, a highly sensitive sniffer, is monitoring the flow. Helium atoms are incredibly small. If there's a microscopic pore in a weld, the vacuum pulls the helium through the metal, the mass spectrometer detects it instantly, and you've found your leak.
It is an incredibly precise form of verification.
It is.
Okay, so the vessel has survived the crucible, the engineering math holds up, the material certificates are perfect, the radiograph film is clean, the pressure test was successful, the beast is securely in the box.
Safe and sound.
Now, this massive physical effort must be translated into a binding legal reality. This brings us to the documentation, the stamping, and the role of the authorized inspector.
This is where all the metallurgy, the physics, and the labor culminate into accountability. The manufacturer is required to draft what is known as the manufacturer's data report.
What is that exactly?
In the ASME system for a Division I vessel, this is the Form U1. In British standards, it's known as a Form X. This document is not merely a shipping manifest.
It's a legal document.
It is a legally binding, signed declaration that every single requirement of the pressure vessel code, from the design stress calculations to the welder's continuity logs, has been rigorously met.
But the manufacturer doesn't just get to grade their own homework, right? I can easily see a shop manager signing a U1 form just to get a delayed vessel at the door and collect the invoice.
That would happen every day if they could.
Enter the AI.
The authorized inspector, or AI. The AI is the linchpin of the ASME safety system. They are an independent third-party inspector who holds a specific hard-earned commission from the National Board of Boiler and Pressure Vessel Inspectors.
But they don't work for the shop.
Crucially, the AI does not work for the manufacturer. They work for an authorized inspection agency or an insurance company. Their sole allegiance is to the integrity of the code.
Our sources detail how the AI interacts with the shop floor through an inspection and test plan, an ITP. And this plan is full of what are called hold points.
Yes, the hold points.
The hold point is exactly what it sounds like, right?
It is a mandatory stop sign in the manufacturing process. The manufacturer must physically halt production, put the welders on standby, and notify the AI.
So they literally just wait.
The shop cannot proceed until the AI physically walks the floor, verifies the specific step, whether it's inspecting the root gap fit up before welding begins, reviewing the radiograph film, or witnessing the hydro test, and signs off on the ITP.
What happens if a shop foreman is in a rush on a Friday night, hits a hold point for a root fit up, can't find the AI, and just tells a welder to go ahead and fill the joint?
Oh, that's a huge mistake.
Really?
The AI has the ultimate authority to make them cut it open. If you weld past an AI hold point without their explicit waiver, the weld is invalid.
Even if it's a perfect weld?
Even if it's perfect. The AI will demand that the shop gouge out the weld metal or perform 100% volumetric NDE at the shop's expense to prove the joint. The AI is the final gatekeeper. Only when the AI has reviewed the material test reports, the WPS, the NDE reports, and witnessed the final pressure test, will they sign the manufacturer's data report.
And only with that AI signature is the manufacturer legally allowed to physically apply the ASME code symbol stamp to the vessel.
Yes, the famous U stamp for pressure vessels, S for power boilers, or V for safety valves.
Right.
This stamp is physically hammered or permanently etched onto the vessel's stainless steel nameplate alongside vital data. The maximum allowable working pressure, the maximum and minimum design temperatures, the materials of construction, the radiography level, and the year it was built.
It is genuinely amazing to me. You have this towering engineering marvel weighing hundreds of tons, holding back terrifying amounts of explosive energy, and it all culminates in a simple 8 by 10 inch square of metal bolted to the shell.
But that little nameplate represents thousands of hours of documented, verified, and audited labor. It is the physical proof of the safety chain.
And I know other regions handle the legal side slightly differently. Our sources mention the European Pressure Equipment Directive, the PED.
The PED is the legal framework for the European market, and it takes a slightly more holistic risk-based approach.
Risk-based, meaning what?
Instead of a one-size-fits-all inspection mandate, the PED classifies the hazard level of the equipment based on the product of the volume and the pressure.
Oh, that makes a lot of sense.
It also considers the state of the fluid. Compressed gas is treated as vastly more dangerous than liquid, and it factors in the toxicity or flammability of the contents.
Right. A 100-gallon tank of compressed hydrogen is fundamentally more hazardous than a 100-gallon tank of warm water at the same pressure.
Exactly. Based on that hazard classification, the PED dictates different modules for quality assurance and dictates the required level of involvement of a notified body, which is the European equivalent of the authorized inspector.
So the paperwork is different.
But while the bureaucratic mechanics differ slightly, the global philosophy remains identical: independent verification of a rigorous safety chain to protect the public.
Now, before we wrap up, we have to talk about what happens after the vessel leaves the shock, because the story doesn't end when the U-stamp is applied.
Far from it.
These vessels go into service in harsh environments: refineries, chemical plants, paper mills. They corrode, they crack, they get modified. Our focus notes bring up the NBIC and R-stamp work.
Repairs are a whole different beast.
Right. If a vessel wall thins out due to corrosion after 10 years, a plant manager can't just call a local auto body welder to slap a patch plate over the thin spot, can they?
Absolutely not. Modifying or repairing a stamped pressure vessel is an incredibly delicate operation governed by the National Board Inspection Code, the NBIC.
The NBIC.
The company performing the repair must hold a specialized R stamp.
Why is it so specialized?
The danger of welding on old vessels is that the steel has aged. It may have suffered hydrogen embrittlement, or the microscopic grain structure may have altered due to years of high-temperature service. You are no longer welding on pristine, known material from a mill.
So how do they handle it? If they need to add a new nozzle to an existing column, what's the procedure?
They have to re-verify everything. They must determine the original material specification, often referring back to that original U1 data report kept on file for decades.
Oh, so that paperwork from 20 years ago suddenly matters again.
Exactly. They must write a specific repair WPS. If they are welding a flush patch, the new plate material must be fully traceable. The welds must be subjected to NDE, and a new pressure test or a rigorous alternative NDE regimen must be approved by an authorized inspector.
So it's the whole safety chain all over again.
The R-stamp process ensures that a repair doesn't inadvertently destroy the integrity of the original U-stamp design.
And as the absolute final line of defense, after the design, the welding, the NDE, the inspections, and the repairs, we have relief devices.
The last resort.
Pressure relief valves, or PRVs, and rupture discs.
The relief device is the mechanical failsafe. If everything else goes wrong, if a cooling water pump fails and the reactor temperature spikes, or if a control valve gets stuck wide open and high-pressure gas floods into a low-pressure tank,
The pressure shoots up.
the pressure inside the vessel will rapidly exceed the design limits. The pressure relief valve is designed to physically pop open at a specific set pressure, venting the excess volume and energy out of the vessel before the steel yields.
But the sources warn about blocked outlets and discharge piping issues. A PRV popping open is great, but that explosive force has to go somewhere.
That is a massive operational hazard. If a PRV discharges into a flare header system, but that header is blocked by a closed isolation valve downstream, the pressure has nowhere to go.
So the valve pops, but nothing leaves.
The vessel will overpressurize and fail anyway. Alternatively, if the discharge piping isn't properly supported, the massive thrust force of the escaping gas can physically tear the valve right off the top of the vessel.
Rip it clean off.
Yep. Relief devices require meticulous maintenance, periodic testing to ensure the springs haven't corroded shut, and flawlessly designed discharge routing.
We have covered incredible ground today. We've gone from the theoretical calculations of maximum shear stress to the atomic diffusion of hydrogen in a weld puddle, and right down to the explosive reality of a pneumatic test.
It's a massive subject.
It really is. But as we bring this deep dive to a close, looking over our notes on human factors, There is a sobering undercurrent to all of this brilliant engineering.
There is, and it is the most critical takeaway. We can spend hours debating the merits of Division 1 versus Division 2. We can demand EN 1043.1 material certificates, and we can deploy the most advanced ultrasonic phased array NDE equipment in the world. You can have the most brilliant mathematical algorithms, the most expensive steel, and an army of authorized inspectors. But this entire imposing system is built on a fragile foundation of human integrity.
Human integrity.
Yeah. If a shop floor manager, driven by ego or a punishing Friday shipping deadline, bullies a welder into skipping a mandatory 3-hour preheating cycle,
Or if a fitter decides to aggressively grind out an undercut rather than report it.
or if an overworked inspector, exhausted at the end of a 14-hour shift, pencil whips a sign-off on a radiograph they barely squinted at, the entire mathematical safety chain shatters.
All the math in the world can't save it.
Exactly. The true safety of a pressure vessel, the barrier keeping that stored energy from leveling a plant, ultimately relies on the invisible ethics of the people who design, build, and inspect it. You cannot write a mathematical formula to calculate for a lack of integrity.
That is a profound and unsettling truth. The greatest engineering in the world is useless without the discipline to execute it. School taught you engineering. The shop floor will teach you wisdom. Stay hungry in teaching. Don't forget, if this helped you even a little, let us know. We're putting this out for free, no paywall, no subscription, nothing locked behind the card. That only works if we know it's actually reaching and teaching. If you're on a journey trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing.